Imagine throwing a ball at a wall. What happens? The ball hits the wall and comes back. It cannot pass through the wall. That is how our everyday world works. But now imagine a world where the ball has a small chance of appearing on the other side of the wall without breaking it. Sounds impossible? Welcome to the quantum world. Today, we are going to understand one of the strangest and most fascinating ideas in modern physics: quantum tunneling. In classical physics, the physics of cars, balls, and humans, an object must have enough energy to cross a barrier. To jump over a wall, you need enough strength. To climb a hill, you need enough energy. If you do not have enough energy, you fail. But in quantum mechanics, particles like electrons, protons, and atoms do not behave like solid balls. They behave like waves. And waves do something very strange. When a quantum particle reaches a barrier, part of its wave enters the barrier. The wave does not stop instantly. It slowly fades inside the barrier. If the barrier is thin enough, a small part of the wave appears on the other side. This means the particle has a chance of crossing the barrier even when it should not be able to. This phenomenon is called quantum tunneling. It is not guaranteed, it is only a probability. Now, why does this happen? In quantum physics, particles do not have fixed positions. Instead, they are described by probability waves. So we do not say the particle is here, we say the particle has a probability of being here and even there. Because of this uncertainty, the particle can borrow a little energy, cross the barrier, and appear on the other side. This never happens in classical physics, but it happens all the time in the quantum world. Now let us look at real-life examples of quantum tunneling. First, nuclear fusion in the Sun. Inside the Sun, hydrogen nuclei strongly repel each other. According to classical physics, they should never fuse. But quantum tunneling allows them to tunnel through the energy barrier, fuse together, and release energy. Without quantum tunneling, the Sun would not shine. Without the Sun, life on Earth would not exist. Second, the scanning tunneling microscope. Scientists use a machine called a scanning tunneling microscope to see individual atoms. A very sharp metal tip is brought extremely close to a surface. Electrons tunnel through the tiny gap between them and create a current. By measuring this current, scientists can see atoms. Quantum tunneling allows us to see the invisible. Third, modern electronics. Tunnel diodes, transistors, and flash memory all depend on quantum tunneling. As electronic devices become smaller and smaller, tunneling becomes more important. Engineers must control quantum tunneling to make modern technology work. Fourth, quantum computing. Quantum computers use tunneling to move particles between energy states. This allows them to store information and perform powerful calculations. Quantum tunneling is one of the foundations of future technology. Now let us talk briefly about the mathematics, without heavy formulas. In quantum mechanics, we use the Schrödinger equation to describe how particles behave. When a particle encounters a barrier, the equation shows that the wave decreases inside the barrier but never becomes zero. That is why tunneling is possible. The thicker the barrier, the smaller the tunneling probability. The heavier the particle, the smaller the tunneling probability. Electrons can tunnel easily, humans cannot. So let us summarize. Quantum tunneling means particles can cross barriers they should not cross. It happens because particles behave like waves. It powers the Sun, modern electronics, microscopes, and quantum computers. Quantum tunneling shows us that nature does not always follow common sense. At very small scales, the universe plays by very different rules. Thank you for watching.